So this is a lecture video, probably one of two, that covers acids and bases. So we're going to be talking about two different definitions of an acid and base. So the first definition that students in this class has to be aware of is the Arrhenius definition of acid and a base. So an Arrhenius acid, which is shown here, it says it donates hydrogen ions to the solution. So if you look at this example here, as you can see, nitric acid, okay, donates a hydrogen ion to solution. An Arrhenius base, on the other hand, donates hydroxide, which is a polyatomic ion, to the solution. And as you can see, sodium hydroxide, it dissociates into the sodium and the hydroxide ions. This is another example of an Arrhenius acid, and the reason why I know it's an Arrhenius acid is, as you guys can see, hydrogen chloride is more. This is actually an accurate name for it, hydrogen chloride, if it's a gas. We can also call this hydrochloric acid. In water, it actually creates the hydronium ion. Very, very important note. The hydronium ion, H2O plus, can sometimes be abbreviated as H plus. So H plus and H3O plus is the same, okay, for our purposes in this class. All right. So there's actually a shortcut about the Arrhenius acid and acid and base definition, and that is any compound that has a hydrogen at the beginning of a compound is an acid. Okay, so hydrochloric acid has an H in front, phosphoric acid has an H in front, hydrosulfuric acid has an H in front, and obviously nitric acid has an H in front. And inversely speaking, any compound that has an OH, a hydroxide ion at the end of the compound, is a base. So magnesium hydroxide, ammonium hydroxide, aluminum hydroxide. You can see all of this have OHs at the end. All of this have H's in the end. Okay. There's only one exception, water, because water has an H in front and an OH in the back. In terms of Arrhenius acid and definition, okay, Arrhenius acid and base definition, it is not neither an acid and a base. It's actually both, if you think about it. So, and actually that's why one of the reasons why water is the basis for neutral solutions. Okay, so if you see water, okay, even though it has an H in front and OH minus at the end, you know, obviously that negates the acid and base at one point. All right, so that's the Arrhenius acid and base definition. The second definition is the Bronsted-Lowry acid and base. And the Bronsted-Lowry definitions of acid and bases revolves around the hydrogen ion in this case. The hydrogen ion is also called protons. So H plus, H3O plus, protons, in terms of acids and bases, are the same. And in the Bronsted-Lowry acid and base definition, what happens is acids are hydrogen donors, or hydronium donors, or proton donors, if you want to use all three names. And bases, on the other hand, are acceptors. So bases are proton donors, proton acceptors, hydrogen acceptors, or hydronium acceptors. So if we look at this one again, so in this case, you always have, in a Bronsted-Lowry acid-base definition, you'll always have both, okay, reacting with each other. So in this case, water is the Bronsted-Lowry acid because, as you guys can see, at the product side, what happened to water? It has lost a hydrogen atom, okay? Whereas ammonia in this case actually becomes the ammonium ion. It's a base because why? Let's look at the red H right now. It has gained that hydrogen ion. So very easy, okay? And if you look at the product side, anything that becomes more positive is the base. Anything that becomes more negative is the acid. Why is this negative and positive? The reason why is hydrogen, a proton, or the hydronium ion, is positively charged. So if you gain something positive, you become positive. If you lose something positive for water, you become negative, right? So that's the Bronsted-Lowry definition of an acid and a base. Okay, based on this relationship, anything can become an acid and base. It has nothing to do with whether you have a hydrogen in front or a hydroxide at the end. You can force an acid to actually react like a base, or you can actually force a base to react like an acid. And the reason why that is it's obviously about strength. I'm sorry about that. Okay, so here you have two acids mixed together. We have phosphoric acid, which is an acid, and hydrochloric acid, which is an acid, right? However, hydrochloric acid is a strong acid. Okay, it's actually in your exam reference sheet. There's a list of strong acids and strong bases. And phosphoric acid is a weak acid. So in this case, since this is a stronger acid, this will lose its hydrogen more readily than this. And since this is a weaker acid, it's now going to act like a base. This is then going to gain a hydrogen ion. So just like the rules that we have here, phosphoric acid that has gained a hydrogen will now become H4PO4 plus. It has become positively charged because it has gained a hydrogen which is positively charged. And chlorine, the chloride ion in this case, has become negatively charged. Why? Because it has lost something that is positively charged. Okay, so again, make a mental note that in the Bronsted-Lowry acid-base definition, you can always force an acid. Like, it doesn't matter whether you have an H in front or OH at the back. The key is it's all about where is that hydrogen going to end up. Whoever loses a hydrogen is the acid. Whoever gains a hydrogen is a base. And when we talk about losing and gaining, we are looking at the product side of the equation. All right? Which brings us to this scale called the pH-POH scale. So you probably heard about pH before. I don't know if you have. So vinegars are acidic in solutions, okay? You probably heard about the terms basic and acidic. All of these things is about the pH or POH scale. Now, the pH scale goes from 0 to 14, and the POH is just flip. It goes from 14 to 0. And the reason why that is the sum of the POH and pH, generally speaking, most of the time, will always equals to 14. Okay, and all of the scale is talking about the ratio between hydrogen ions, which are also called hydronium ions, which is the same as protons, and hydroxide ions. Okay, so at pH of 7, the amount of hydrogen and hydroxide ions are equal, as shown here. So water has a pH of 7. Why? Because at that pH or POH, the number of hydrogen ions is equivalent to the number of hydroxide ions. And again, please remember, hydrogen ions is the same as hydronium, is also the same as protons in this case. Okay? Anything, if you can see here, anything at this red area here, and actually this is dependent upon litmus paper, and anything that's on the blue, okay, anything on the side, okay, of the 7 scale, so that means anything below 7 in terms of pH is called the acid, the acidic side, and anything on this side is called the basic side. The reason why this side is acidic is because there are more hydrogen than hydroxide ions. Okay, so remember, before at the pH of 7, hydrogen and hydroxide ions are equivalent, right? So once you start having more hydrogen than hydroxide ions, your pH is now below 7. Okay, now make sure that you also understand that this side, the pH of less than 7, which is acidic, is also the same as a pOH above 7. Again, because there's an inverse relationship between pOH and pH. Inverse relationship means when the pH goes down, the pOH goes up. Okay? Similarly speaking, on the blue side, which is the basic side, that means you have more hydroxide ions than hydrogen or hydronium or proton ions. Okay? So again, inversely speaking, okay, the pH in this case is going to be above 7, and the pOH is going to be less than 7, right? So there's going to be generally some exceptions about the number 14, but that's going to be rare, and it depends upon the strengths of acids and bases. But please, 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 please understand the relationships between these scales and the amount of hydrogen and hydroxide ions. Okay. So we're going to do some math to do some calculation. I'm going to move this around a little bit so that you know, hopefully, oops, oh boy, all right. This is actually your exam reference sheet, and this shows you how to move between unit concentrations. Okay, so in here it says what is the pH of a 0.5 molar hydrochloric acid solution. Now, if you see here, hydrogen ion concentrations, okay, is the same as molarity of hydrochloric acid, okay, or H. So in this case, this is an acid. So in solution, this compound is gonna give off hydrogen ions, right? And we're gonna be assuming that this is an aqueous solution, okay? All of this is gonna be aqueous solutions. What does that mean? So you have to think about this, ladies and gentlemen. So remember, water had hydrogen ions is the same as is the same quantity as hydroxide ions, okay? If I put in water a 0.5 molar hydrochloric acid solution, now what's going to happen is now you're going to have more hydrogen ions, right, than hydroxide ions, and that is why the pH of this solution should be less than 7. Or the pOH of the solution should be greater than 7, because there's an inverse relationship between pH and pOH. That means to say when the pH is below 7, the pOH has to be above 7. Okay, so I'm just going to erase this very quickly. So what this means to say is this starts here, so we're here, and what we're trying to do is we're trying to go to pH. So we're going to go from here to here, and as you can see, the formula that you need to use is follow the arrow. pH equals the negative log of the hydrogen ion concentration. Negative log 0.5 equals 0.3. So the pH of the solution is 0.3, which is less than 7. Okay, if your number that you came out, the pH is greater than 7, that means you had something wrong. In your calculator, especially at TI-30X, you need to plug 0.5 first, then take the log base 10, and then you take the negative. You cannot plug this in order in your TI-30. You cannot put negative log, it's just going to give you an error, okay, or sometimes 0. You need to put 0.5 first, take the log, then take the negative, and you should get 0.3.